Hello, and welcome to Physics Video Optics.1 Ray Model, Reflection, and Image Formation. In this video, we will begin our study of light by looking at ordinary occurrences and explaining what is actually happening to allow us to see things the way we do. While we know that light is a wave and therefore follows the rules of wave behavior that we've studied previously, to begin with, we will simplify light motion and assume that light always travels in straight lines, or what we call rays. And then we will use geometry to analyze the motion of light as it interacts with objects around us. When we look at an object like a pencil sitting on a desk, we can see it because light rays are bouncing off the surface in all directions, and some of them end up going into our eyes, as seen here. And then our eye does its job and our brain interprets it, and we'll come back to that later. We use the idea that light is traveling in straight lines to illustrate the fact that we have light bouncing off in all directions, and it's easiest for us to focus if we draw them as a ray. The direction of each ray is determined by where the source of light is and the shape and texture of the pencil. It is important to remember that we see objects that do not create their own light, like a pencil, because of reflection. So that's where we're going to start our unit of light. We will refer to them as light rays, and we'll start with reflection. If we think about light hitting a smooth surface, we can focus on one ray of light and how it interacts with that surface. As shown here, we have a source of light. Maybe it's a light bulb. And rather than showing all of the rays, we're just going to show one. We draw the light ray coming in to hit our surface at an interaction point here. And we then measure what we call the angle of incidence from the normal to the surface. Now remember that the normal line, as we've talked about it in other units, is a line that is perpendicular to our surface. So when we are measuring angles in this unit, we need to make sure that we're measuring them with reference to the normal and not to the surface itself. So we have the angle of incidence, the angle in which the light comes into the surface, and then we have the angle of reflection, the angle to which the light reflects off of the surface. This simplified version of what light does when it gets to the surface allows us to clearly see the law of reflection. The law of reflection says that the angle of incidence is equal to the angle of reflection. This holds true even if the surface is not smooth. So as long as we remember to measure the angle of incidence correctly from the normal, we can easily find out the direction that the light will travel in after it has bounced off of a surface. Now, if we take a look at this, we have a very rough surface here, and the rough surface has a light source up to the upper left-hand side somewhere, and the light is coming down and it's hitting the surface. Now, for each one of these interaction points, the angle of incidence is equal to the angle of reflection at each particular point. It doesn't look like all of these rays are going to make it to our eye, and in fact they are not. When it occurs like this, when we have a rough surface, this type of reflection is called diffuse reflection. So every individual ray will reflect off based on its own theta I, which is why we sometimes get things like glare or distortion from reflections. The surface is not nice and smooth. Now remember, this smoothness needs to be present on the molecular level, not just for our sight or for our touch. So as you can see here in this picture, it's a little bit less cluttered. The eye in both of the two different positions shown here will see the reflected light, even though it's diffuse reflection, because the light's being pretty much scattered on the other side. The other type of reflection that we see in terms of like a mirror, for example, is what we call specular reflection. With specular reflection from something like a mirror or a very smooth piece of metal, the light all reflects off towards one particular place. So the person who's a little bit higher or a little bit closer is not going to see the reflection that the person that is back here sees, because all of the light goes to one point. Whereas if it's a rough surface, then multiple people can see it at the same time. Let's take a closer look at this specular reflection, and in particular, let's look at it with respect to a mirror. What you see when you look into a plain flat mirror is an image. This image appears to be behind the mirror, and this is because our brain cannot tell that light reflected off of the bottle, and when it reflected off of the bottle, it reflected to a surface and then reflected back again. Our brain can't interpret it that way. It assumes that the light comes into the eye from straight lines, and therefore the object, our bottle in this case, the brain interprets it as being behind the mirror, the same distance as the object is in front of the mirror. And again, this is a plane mirror, this is a nice flat mirror. So our brain consists of an amazing amount of neurons and things that can interpret lots of different things, but this is one that the brain gets confused by. It can't understand all the reflection of light. So our image is over here behind the mirror. Now there's no way that we could actually put a piece of paper here and have the image formed on that piece of paper, because it's really within the mirror, it's a reflection within the mirror. So because we can't display this image on a piece of paper located at DI, this is called a virtual image. The distance of the image from the mirror, as I said before, is equal to the distance of the object from the mirror. So this brings us to an interesting question. How large does a mirror need to be in order for us to see our entire body in it? If a small one can be used to see a small object, do we need to have a really big one to see the rest of us? Let's take a look. To answer the question how large a mirror must be and where it must be positioned, we need to set some parameters to work with. So let's say that this woman is 1.6 meters tall and her eye is 0.1 meters from the top of her head. In order for her to see her whole body, the light ray from the top of her head and the one from her feet must reflect off the mirror and enter her eye. So light ray GF must reflect into her eye, as must AB reflect into her eye. Let's start with the ray AB at her feet. It reflects off the mirror at point B and makes it to her eye, which means that the lower half of the mirror, if there were to be a mirror down here, is doing nothing. So in fact, we don't need a mirror down there. Our lowest height of the mirror would need to be at point B. Okay, well, keep in mind that theta I equals theta R, the angle of incidence equals the angle of reflection, as we just said a minute ago. So those two angles are equal to each other. So what that means then is that dB must be equal to half of AE because of similar triangles. Now remember, E is to the eye. Similarly, if we look at the top of her head, the mirror only needs to reach to half the distance from her eye to the top of her head, which would be 0.05 meters, which is point F. So therefore, DF is equal to 1.75 meters. And the mirror needs to have a vertical height of 1.55 minus 0.75, 0.8 meters. And again, the 1.55 comes from it being the height from D to F. But notice that 0.88 meters is half of the woman's height. So in order for you to see your whole body in a mirror, the height of the mirror needs to be half of your height, and it should be placed, as we figured out before, here, it should be placed halfway, the bottom of it should be placed halfway between your height and the height of your eye and the ground, which in this particular case is 0.75 meters off of the ground. Try this at home. If you have a large mirror, stand at a point where you can see your entire body. Mark on the mirror where the top of your head and where your feet appear to be. Then move closer. Do these locations change? Move back. Do they change this time? And can you figure out why this happens using this geometric analysis? Let's take a look at an example similar to that whole idea of how big does your mirror have to be and where do you have to stand. A person whose eyes are 1.72 meters above the floor stands 2.20 meters in front of a vertical plane mirror whose bottom edge is 38 centimeters above the floor. What is the horizontal distance x to the base of the wall supporting the mirror of the nearest point on the floor that can be seen reflected in the mirror? So in other words, how far from the wall can you see in the mirror? Well, let's put some information down here. We know that the eyes are 1.72 meters above the ground, but we know that the mirror is 38 centimeters off of the ground. So the length of the mirror is 1.72 minus 0.38, which is 1.34 meters. So this part here is 1.34 meters. Remember that the law of reflection says that theta I equals theta R. So these angles being equal and these two triangles here being right triangles means that we can use similar triangles to solve this, to figure out what x is. So we can say then that 2.20 is to 1.34 as x is to 0.38. Cross multiply and solve for x, and we find out that this person can see up to 0.62 meters away from the wall just by looking in the mirror. If you can keep the law of reflection in mind, along with remembering your geometry of similar triangles, a lot of the problems that we're going to do are going to be quite simple for you. Let's do another one. The disks of the sun and a full moon are about, oh, I've forgotten a T, sorry, are about the same size in our sky. The diameter of the sun is 1,392,000 kilometers, and the diameter of the moon is 3,475 kilometers. If the moon is approximately 384,400 kilometers from the Earth, estimate the distance to the sun. All right, well, in order for the disks to appear to be the same size to us, they must subtend the same angle to our eye. In other words, when we look up at the sky, then the moon must fill the same space in our eye as the sun does. Bit of a demented looking person there, but this is an eyeball. All right, so let's see, what do we know? We know that the sun's diameter is 1,392,000 kilometers. We know the moon's diameter is 3,475 kilometers. We know that the moon is 384,400 kilometers from the Earth. The question is, how do we estimate the distance to the sun? Well, if we take a look at this, we can, our eye is obviously significantly smaller than this in real life. So since these two objects subtend the same angle in our eye, that must mean that we have similar triangles again. So we can set up ratios of our similar triangles between the radii of the objects and the distances they are from our eyeball. So if we start with the moon, 1/2 times 3,475 is 384,400 as 1/2 times 1,392,000 is 2x. Well, the 1/2s go away. We cross multiply and solve, and we end up with the distance to the sun being 153,981,273 kilometers, or approximately 154 million kilometers. Now, the real distance between the sun and the earth on average is 149.6 million kilometers. So our estimate of using similar triangles and their radii and the distance between the objects is pretty close. Not too bad at all here. So essentially what we're doing in this unit is making sure that we have an understanding that light can be considered a ray, that light reflects off of surfaces the same way, whether it's rough or smooth, using the angle of incidence equals the angle of reflection, and that images can be formed depending on what the surface is, and those images that are formed from mirrors are what we call virtual images, because we cannot actually put a piece of paper or a screen where the image is supposed to be and see it formed on that paper there. Bye for now.